Hello everyone, this is Dr. Young, and in this video we are going to introduce to you just a generic electrophilic aromatic substitution reaction, the EAS reaction, and talk about activators and deactivators, what sort of help this reaction occur more quickly, what will slow these reactions down. So first of all, right, electrophilic aromatic substitution, EAS, we just abbreviate EAS, just like SN1 instead of nucleophilic substitutions that are second order. And what's going to be different about this is kind of a nice little self-contained unit, because the previous reactions that you learned are not going to work on these types of compounds for the most part, right? So like if you had something like a benzene ring, it may look like an alkene to you, right? Like we've got 3 alkenes, but if you do things like you add HBr, right? We added HBr or HX just in general to alkenes. We saw reactions with those. We would do things like hydroborations, right? Add BH3 and peroxides and hydroxide and stuff like that, right? And water. We would do things like add, or maybe we could do, H2 and palladium on carbon. Or we might try to do things like, I don't know, ozonolysis. Any of those sorts of reactions that we used to know how to do on alkenes don't work, right? So we were not going to see any reaction because, as we've talked about before, right, you've already learned, aromatic compounds are particularly stable and are not as reactive as like a normal linear triene would be, right? Because those electrons are so delocalized. So what we're going to see is that we are going to be doing instead these electrophilic aromatic substitutions, these EAS reactions. And I'll just give it to you just in general what this looks like here, and then I'll draw the mechanism. In general, what this is going to look like is that we have your benzene ring, or any aromatic compound. We're going to stick with benzene. And then you add some sort of super electrophilic something, and we'll talk about what those super electrophiles are. And what you do is you replace one of the hydrogens that was on that benzene ring, and you replace it with your electrophile. That's all it really does. And so I'll draw this H here just so we can kind of see it. But the idea is that we are substituting, right? Hence the S in this, the substitution. We're substituting out a hydrogen on a benzene ring. We're replacing it with some super electrophile. And the thing that we're using to replace it with is an electrophile, not a nucleophile. So it's not like a SN1 or SN2 where the things that came in were nucleophiles. This is a electrophile. Now the general mechanism here, and this is going to be the mechanism for all of them, the core mechanism, and I'll show you more of how we make electrophiles later. But if I take a plain benzene ring, and I'm just gonna leave this generic to us, just some kind of really good electrophile, just E+. You want to recall, right, that aromatic rings, they have a whole bunch of these pi electrons, right? They have more electrons in that ring than you would normally if you had like a cyclohexane, for example. So you can think of alkenes and these aromatic compounds as being nucleophiles. They're going to be sources of electrons. They have free electrons to donate to things. And that's what we see in this very first step, is that our aromatic ring is going to go get our electrophile. And when you do that, you lose aromaticity, right? So I'm going to do this. I'm going to pick this up. Now I'm going to have a hydrogen and my electrophile on one carbon, and I've got the carbocation on another one, right? So it's kind of like an addition to an alkene. Now, one way that this is different from the addition to an alkene is that now I've got a whole bunch of resonance contributors that I could draw. And I'll just draw them out for you here real quick, right? I can move this positive charge around the ring, so it gets nice and stabilized. So it's a reasonable intermediate to propose. Oops. So you get this intermediate, right? 3 structures. It's all really one molecule, but here's the 3 different ways you could draw it. Here's my 3 contributors. And what we're going to see is that this last step is kind of like an E1, where I've got a positive charge. I don't have anything else that can add to that positive charge. But the issue here, right, is that I started with something that's aromatic, and now I have something that is not aromatic. It's not aromatic at all, right? It's non-aromatic. And when I lose that aromaticity, I lose a lot of stability. And so our last step is going to be to regain that aromaticity. So in my last step, we're just going to lose a hydrogen so that we make that double bond again, and now we are aromatic once more. All right, so now I'm aromatic again, That electrophile is still on there, but I released an H+. So these reactions just, again, replace a hydrogen with whatever that electrophile is. And that's our basic mechanism for what's going to be all of these reactions, whether it's a chlorination, iodination, a Friedel-Crafts alkylation, a sulfonation, all of these things that we'll talk about in the future videos. That's the basic mechanism. The only difference is going to be what that E is, what that E+, that electrophile is. So that's your basic electrophilic aromatic substitution mechanism. Now, what I also want to talk about in this introductory video is activating and deactivating groups, or activators and deactivators. Because I will definitely ask you a question like, rank these in order of increasing a rate with an electrophile, or which is the most activated, or which one's going to be the fastest. And so I'll give you 5 compounds like this, right? And right now you might just be looking at those and be like, well, I don't know what we're going to talk about. I don't know how to rank those. But you actually already have all the skills to interpret this, right? Because you know that you're going to react with increasing rates. And we know that the aromatic rings, are going to act as nucleophiles. Right? We saw they went to go get that electrophile. And if they're going to act as nucleophiles, that means we want them to be electron rich. The more electron rich they are, the more negative they are, the more they're going to attract that positive electrophile. And the easier it's going to be to form that carbocation intermediate, right? If you're really electron rich, you can stabilize a carbocation intermediate. So our activators, I'm just going to write this down here, right? Our activator groups are going to be things that donate electron density to the ring. Right? And by activators, we mean things that are going to speed up those electrophilic aromatic substitutions. They're going to go faster if you try to do them on a ring that is already electron rich. Now our deactivators are going to withdraw electrons. They withdraw electron density. And by withdrawing electron density, right, they make those nucleophiles less negative, so the nucleophiles are less attracted to the positively charged electrophiles, and then that carbocation intermediate that I showed is now less stable, it's higher in energy, because you're withdrawing electrons from a cation species. And so that's going to slow down. It's going to slow down these EAS reactions. So let's look at these. I've got 5 compounds here. Let's take a little closer at these, take a closer look and decide which ones are actually activators and which ones are deactivators. Which ones have been activated and which ones have been deactivated. So I just kind of blew these up here. I put this one here, right? Here's just plain old benzene. And this is just going to be our benchmark, right? This is going to be, we're going to compare everything to benzene. That just has H's on it. We'll see how everything else behaves. Now, if I look to the next one over, right, that's toluene. It's just got a methyl on there. And if you go back and remember, right, with methyls, we treated methyl groups, just alkyl groups, as weak electron donors, right? So this just has a methyl group on here. It's just a CH3. And we said that alkyl groups, and we'll put that note down here, alkyl groups are weak electron donating groups. Right, because they work through something akin to induction, right? The hyperconjugation. It's not, they're not going to delocalize anything, right? There's no resonance contributors I need to draw, but we know that they donate electron density into a ring is the idea. So we're just going to leave that at that. So if anything, that seems like that's going to help, right? We're donating electrons in. That means that aromatic ring is going to be a little bit more negative with that methyl than without. Now, if I look at this second one here, I think I've already taken up too much space, but that's okay. I look at this second one, I've got a ketone on here, right? I've got a ketone, this is acetophenone. If I look at this one, I can actually draw a resonance structure here where these electrons move to form a double bond between those 2 carbons, and that kicks up electrons up onto this O, which is going to give me a resonance structure that looks like this. But what you can see, right, with this resonance structure is that we are literally taking electrons out of the ring and they're going up into the oxygen. So this would be a withdrawing group, right? We're taking electrons out of the ring. Plus, you can see I'm starting to put a positive in the ring already, right? And we just said I don't want my ring to be positive. I want my ring to be negative because the rings are the nucleophiles. They should be negative, not positive. So this group is going to be considered a electron withdrawing group. And then because it's doing it through delocalization, right? We have resonance structures. Because it's happening through delocalization, that means it's going to be a strong electron withdrawing group. Strong electron withdrawing group. Right, and again, that's because we're talking about delocalization. The electrons from the ring are going up into the carbonyl, right? It's taking away those electrons. Now, if I look at the NH2, if I look at the aniline here, it's similar but opposite. So because I have a lone pair on that nitrogen, this lone pair can drop down and put electrons into the ring, right? So it's just the exact opposite here. So now I can have a double bond between the nitrogen with its two hydrogens. That makes it positive. But what I'm able to do is I'm able to put electrons into the ring, making it more negative, right? Here's one resonance contributor. I'm not drawing all the resonance contributors for these just to save space and time. I just wanted to show you how this nitrogen, because it has lone pairs on it, can donate electrons into the ring here. And so that means it's going to be also an electron donor, like our methyl group over here, but it's donating electrons in through delocalization, right? It's using resonance. You're going to have to draw resonance contributors. So this would be an example of a strong electron donating group. And again, because of delocalization. Because of delocalization. And then lastly, if I look at the chlorine here, it also has lone pairs on it. And now while I could draw a resonance structure where those electrons drop down, maybe I will. Let's just go ahead and do that. Let's say I draw this. It'll be akin to the aniline. So Cl, one of its lone pairs now in the ring. The reason, so while this technically can happen and it's a tiny bit delocalized, right, this is a very, 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 very poor structure, right? Very high energy, right? Because you have a positive chlorine. Very poor structure, or in other words, very minor contributor. Right, so it's not really like it's donating electrons in very well through resonance. The larger effect for this is going to be the fact that chlorine is so electronegative that it's going to be pulling electrons out. Right, chlorine is very electronegative. So it's actually going to be withdrawing using induction. That's going to be its overall effect. That's what we see through the experiments too. And so what we see is that chlorine in this case is going to be a weak electron withdrawing group because it's using induction to withdraw electrons, right? Just because it's so electronegative, it's pulling some of those electrons out of the aromatic ring, making it more positive, making it a worse nucleophile. So here's how you want to kind of like interpret these different groups, right? Like what's happening? And so what I want to do is I want to put this on a chart here in a second, okay? But before I do that, I just want to go through this and make sure we kind of have this like ordering right in our heads. What we're saying here is that toluene compared to benzene, toluene is going to react faster because it has an electron donating group in it, right? So toluene will react faster than benzene because it's more electron rich. But what will react faster than toluene is aniline. Aniline will react even faster than toluene because it has a strong electron donating group on it. And that's because the nitrogen is donating in electrons through delocalization, right? I have actual arrows going into the ring here to show that how much more electron rich this ring gets, right? So both of these would be faster than plain benzene. Aniline would be fastest, the toluene would be second fastest, benzene would be next. And then these last two, right, the acetophenone and the chlorobenzene, those are going to be slower than a reaction with benzene. This would be the second slowest because it's pulling out electrons, but it's just induction. This would be the slowest of all of them because it's pulling out electrons, but it's through resonance. It's through that electron delocalization. So this would be the slowest of all of them. Now what we're going to do in the next page is show you a table where we're going to kind of categorize these so we don't have to look at we don't have to do this for every single group we see. We just want to be able to kind of generally categorize them. So I got this table of my activators and my deactivators, right? And I've divided them between strong and weak. Now, you may find books and stuff that have like medium or moderate activating groups or something like that. We're just gonna put it into two camps: activators, deactivators, strong, weak. We're not gonna deal with this middling stuff. So our strong activators, what we're mostly gonna see for our strong activators is that these are gonna be things with a lone pair at the point of attachment. And by point of attachment, I mean they're attached to the ring, right? So I'm talking about the thing that would be like in a benzylic position, sort of, right? The things that are directly attached to the ring. So we're talking about groups, like I did NH2, that had a lone pair and is attached to the ring. You could do OH, right? You could have a phenol would be really activated, or OCH3, right? Some sort of like ether there. Sulfur containing things. Pretty much anything, most things with a lone pair at that point of attachment are going to be able to donate that in and activate that ring. So oxygen and nitrogen are the most common ones. For our weak activating groups, these are just going to be our alkyl groups. So if it's just a plain alkyl group, sp3 hybridized, C's and H's, nothing too special, just some generic R group, right? It could be a methyl, it could be an ethyl, it could be T-butyl, it could be really whatever you want, right? It could be some weird big long chain with a bunch of branching. Whatever you want. Just some alkyl group, some plain sp3, whatever, right? Because those are just going to donate through induction. They're just going to be weak electron donors. Now for my strong deactivators, these are going to be, for the most part, they're going to have a pi bond at the point of attachment. Or a large positive charge. Or a large positive charge at that point of attachment. So examples of that would be things like a nitro group is a really strong deactivator because that has a positive nitrogen right there at the point of attachment, plus it has a pi bond. I just showed you an example of a carbonyl, right? Whatever your carbonyl is, aldehyde, ketone, ester, amide, whatever. We're going to see in future videos things like adding a sulfonic acid, right? That also has pi bonds at the point of attachment. If you had a quaternary ammonium salt, so nitrogen with extra R groups that became positive, or even something like a CF3, right? That's not a full positive, but that's a really large partial positive. So anything super positive that's attached directly to the ring, or things with pi electrons, they can do that resonance structure where you just pull out so much electron density that you slow down reactions, these electrophilic aromatic substitutions. So that'd be your strong deactivators. And then our last group, the weak deactivators, those are just going to be our halogens. Right? So just your good old halogens. So we're talking chlorine, bromine, etc. Just your halogens, fluorine, iodine. Because they are going to be electron withdrawing through induction, but it's not through, they're not taking things out through delocalization through resonance. So they're just going to be our weak deactivators. And we're actually going to come back to this chart later when we talk about directing groups, orthoparameta directing groups, but that'll be later. So definitely keep this chart. This is a super helpful chart for figuring out how things are, our groups, activators and deactivators, but also how things are going to direct. So that'll be in future videos though. So real quick, if I was to do these questions, right, here's two sets of examples. We kind of already did this first one together, so I'll just kind of re-put our notes on here. We said the alkyl group was a weak electron donating group. We said that acyl group, this ketone here, was a strong electron withdrawing group. We said the nitrogen, because it had a lone pair on it, that was a strong electron donating group. And we said the chlorine, because it was a halogen, was a weak electron withdrawing group. So then if I'm going to put these in order here, where 1 is the fastest, I'd expect this one to be the fastest because it is the most electron rich. It's the most electron rich ring. It's going to have the most attraction to an electrophile when we do the electrophilic aromatic substitution. My second fastest then should be the one with the weak electron donating group. Then it will be my benzene, which has nothing, no activators nor any deactivators. And then fourth should be the one that's only deactivated a little bit. And then lastly, the one that's deactivated the most. So this is the most electron poor. Or another way to say that is the most deactivated. The most deactivated. So why don't you pause for a second. Below I have 5 more molecules. You should pause for a second and see if you can do this with those examples. I'll stop talking for a minute while you pause, and then hopefully you practice this and then come back with me. Okay, so let's look at this together here. If I'm looking at these, right, I just want to categorize them into strong or weak electron donors or withdrawers. If I look at this first molecule, I see that I have a ring attached to my ring, but these are just alkyl, right? These are just alkyl groups. And since it's attached in 2 places, I'm actually going to count it as 2 alkyl groups because I'm attached in 2 places. But either way, those 2 alkyl groups, right, they're both weak. They're both weak electron donors. If I go over here to my nitro group, that definitely looks to me like a strong withdrawing group because it's got a full positive charge and it has a pi bond at that point of attachment. So strong electron withdrawing group. My phenol, I have lone pairs at that point of attachment. So that would be a strong activating group, electron donating group, be a strong activator. Benzene is just my plain benchmark. And then fluorine is a halogen. So I know that that's a weak electron withdrawing group. It's a weak electron withdrawing group, or in other words, it's a weak deactivator. So then if I just go through that, it looks like my most activated is this. That'll be the fastest. Second fastest would be the one with 2 alkyl groups. And by the way, 2 alkyl groups or 3 alkyl groups, they don't compete with like one strong electron donating group, right? They're not going to quite get there. They're pretty weak. Having something that can donate electrons in through resonance is going to be a much larger effect and much more electron rich than having just alkyl groups on something. So even though there's 2, it's not going to beat it. Then my third is going to be benzene, and then my fourth will be just the fluorine, and my fifth would be the one with the nitro group. So that's how we would rank these. And so not only am I going to like ask questions like this and ask you why, just kind of like, do you get electron donating withdrawing groups? But we'll see later that there's certain reactions that don't work if your ring is already strongly deactivated. So you want to be able to identify a ring and be like, oh, yeah, that's activated, so this reaction will work. Or, oh, yeah, that's already too deactivated. I cannot do this reaction on that ring. So keep that in mind. Practice this. There's practice posted online. Happy studying and good luck.